Alright gang, here we go. So this is Chem 2 Unit 5. We're talking about covalent bonding and Lewis structures and bond polarity. Alright, so covalent bonding, last video we talked all about ionic bonding. Remember that it occurs between a metal and a non-metal. Right, in this video we're going to be talking about covalent bonding, which occurs primarily between two non-metals. Okay, alright, and it's all about sharing these electrons. Okay, so remember last time we talked about this word electrostatic. So remember this really means that you're talking about the attraction or the repulsion between charges. Okay, so you know everything that has a charge is either neutral, positive, or negative. Okay, and remember opposite charges attract, like charges repel each other. So within a covalent bond, we have several things going on. We have these protons that are pushing against each other, right? And so they're repulsing each other because they're both positively charged. These would be the nucleus, right? And then we have the electrons are also repulsing each other because they're both negatively charged. But then we also have this attraction between the negative and the positive, and then on four sides there. So this is kind of a rough estimate or a rough diagram of how the bonding actually occurs. So in order to actually have a bond, this attraction force needs to be greater than the repulsion force. And that just makes sense, right? Here's like a representation of what that bond kind of looks like. Okay, so these blue dots that are around here are the electrons themselves that are in their location. Okay, so their electron density. And notice that on the outside we kind of get this kind of shape going. So we kind of have, you know, a strong density here, and then it kind of gets smaller right here. Just kind of tracing the darker portions, and we kind of get this kind of a shape kind of like that. And so this area right here is where the electrons are actually being shared, right? So that's kind of that is the covalent bond itself. All right, let me just make sure. All right, cool. All right. So last time we also talked about Lewis symbols. Remember our Lewis symbols? And they were just the name of the symbol with how many valence electrons they had. So like aluminum, it has 3 valence electrons, so it had 3 dots around it. And you know, we put 4 around it, and then we pair them up after we get to past 4. You know, so on and so forth. Okay, now we're going to be talking about Lewis structures, and this is a way of demonstrating how the covalent bonds make your molecules actually stick together. Okay. And so essentially we're going to use the sneezing tree of the octet rule, trying to make these elements have the same number of valence electrons as their nearest noble gas. Okay, so hydrogen, almost all of them are going to try to get 8, except for hydrogen is the big exception for the octet rule, because helium only has 2 valence electrons, so hydrogen is only going to want 2 valence electrons. And so we've got 2 hydrogens that are put together down here, and we've got this bond here, and this bond represents 2 electrons, right? So we've got 1 electron. I kind of think about it at 1 electron on one end, 1 electron on the other end, so we got 1 on each side here. So this is hydrogen, and because they're sharing these 2 electrons, this hydrogen has 2 valence electrons. This hydrogen here has 2 valence electrons. All right, so it's got the same number of valence electrons as its nearest noble gas, which is helium. So it's all happy sappy. All right, and then we have chlorine. Okay, so chlorine comes in with 7 valence electrons. So here's the 1, 2, 3, 4, 5, 6, and then its 7th valence electron is this guy right here. Okay, right here. This would be its 7th valence electron, and then it's going to get this other, its 8th valence electron from the other chlorine, and so now it also is going to follow this supposed octet rule, okay, and follow these and get these 8 valence electrons, okay. And so that's pretty much a Lewis structure in and of itself. Now, one of the shortcuts you can use to help you figure out how many bonds a non-metal is going to make in a Lewis structure is by counting up how many valence electrons it has. Remember, so each electron is trying to get to 8 valence electrons, and if you subtract out the number of valence from 8, then you get the number of bonds it's going to make, more or less. Okay, so for example, with fluorine here, fluorine comes in with 7 valence electrons, so we can say 8 minus 7, so he's going to make 1 bond. Okay, so there's your 1 bond for fluorine bonding to that hydrogen. We're going to do the oxygen, so we have the 8. Oxygen has 6 valence electrons, so it's going to make 2 bonds, right? And so these are your 2 bonds here, right here, and right here. And then we have nitrogen. Nitrogen has 5. You can kind of see the pattern here. It has 3 bonds, okay, etc., etc. And the carbon has 4 valence, so it makes 4 bonds, etc., etc. All right, and the whole idea is just trying to get to have the same number of valence electrons as its nearest noble gas, and that's known as the octet rule, because primarily they all want 8. Okay, couple of notes: the electrons on Lewis structures. Okay, lone pairs are represented with dots. Okay, and they can only be on one atom. Sometimes you'll see some screwballs that'll try to put more than one dot on each atom, or more than one lone pair, but assign the lone pair to more than one atom. It doesn't work like that. The electrons can only be on one atom at a time. All right, and then the bonding pairs are the shared electrons, and these are represented by a line, and crazy people represent them as 2 dots, but we won't do that because that's a crazy person thing. All right, so really just focus on using lines to represent your dots. Okay, so here's some examples. All right, so and then you can also have multiple bonds. So single bonds are when you have one line or one pair of electrons. So this would be 2 electrons being shared. And then you could also have a double bond, which is essentially having 4 electrons being shared. All right, and then you can have triple bonds, which are 6 electrons being shared. Okay, and these are called multiple bonds. All right, so for example, if we're making carbon dioxide, we've got 2 oxygens and 1 carbon. The carbon's going to go on the middle because it's the least electronegative, so it's going to go there. And then because carbon has 4 valence, we know it needs to make 4 bonds. Okay, so 2 of those bonds will be the single part of the bonds, and the other 2 will be the double part of those bonds. And notice how this looks like a crazy person's writing with these 4 dots right here showing you these electrons. This is the real way to do it over here. All right, so you got your carbon, you got your 2 oxygens on the other side, and your 2 dots. 2 sets of 2 dots on each oxygen. So notice that each carbon, or this carbon, has 8 valence electrons, right? 4 from each double bond, right? And then so the 4 plus 4 is 8. And then each oxygen also has 8 electrons. It's got 4 from the lone pairs, these 4 dots that are on them, and then it's got 4 from this double bond over here. So each oxygen has 8, the carbon has 8, and Bob's your uncle. All right, and then the nitrogen here, nitrogen has 5 valence, remember, so it's going to make 3 bonds, and so it's going to have a triple bond between the 2 nitrogens, right? So you got the 2, and then you got 6 electrons in the middle, and then notice how, once again, a crazy person has used these set of 6 dots in the middle to represent a triple bond. Who the heck does that? Crazy people do. Okay, so we're going to do it like this. All right. So let's try this. We're going to skip practice exercise 1. Okay. We're going to try practice exercise 2. Here we go. So it says compare the Lewis structure for neon with the Lewis structure for methane. All right. How many valence electrons are in each structure? All right. So neon, well, the Lewis symbol for neon is a noble gas, so it's not going to make bonds, and it's got 8 valence electrons. So this is the Lewis structure, or the Lewis symbol for neon. All right, and then it says for the Lewis structure for methane. Well, we know carbon's going to make 4 bonds, and it just so happens that all 4 of those bonds in this case are going to be to these hydrogens, so he's going to be like this. All right, and it says how many valence are in each structure. All right, well, neon has 8 valence. Okay, and this carbon has 1, 2, 3, 4, 5, 6, 7, 8 valence. Nice. And it says how many bonding pairs and how many non-bonding pairs does each structure have? Well, neon has all 4 sets are non-bonding, so it's going to have, these are also called lone pairs. Lone pairs. Okay, so it's got 8 lone pairs, and the methane's got 4 lone pairs and 4 bonds, respectively. So 8 total electrons. All right, now, remember, in a covalent bond, remember ionic bond, in an ionic bond, the electrons are given away, okay? Given or taken, all right? Now, in a covalent bond, that's what we're learning about now, these electrons are being shared, all right? So, but the thing is, just like if I shared an ice cream cone with my 3-year-old, I'm not going to share it equally. I'm going to get more of that ice cream than he is. Okay, so just the same thing with atoms. They are going to share, sometimes these electrons will be shared equally, and both sides will have an equal portion of the density, but in a lot of cases, the electrons are not shared equally. Okay, and we call this bond polarity. Okay, so it's really just a measure of how equally or unequally the electrons are being shared. So in a non-polar bond, they're being shared equally. Okay, and in a polar bond, they are shared unequally. So that means one of the atoms attracts with a greater force. Okay, all right. So here's another way to represent it. So you've got a fluorine elemental fluorine, hydrofluoric acid, and lithium fluoride here. So notice that in fluorine, you got two fluorine atoms right here, and because they're the same thing, they're going to be pulling on these electrons equally hard. This little bar chart up here, color chart, shows us where the electron density is. So if we have a blue area, that means it's really, really low electron density. Red area means high electron density. We kind of get this variation in colors here. Notice that primarily everything in the fluorine, we get a little bit of this light green here, and then the rest of it on the edges is dark green. And so this shows us that the electrons are pretty much being shared completely equally across the whole thing. There's not one side that has definitively more electrons than the other. However, with hydrofluoric acid, notice how on the hydrogen side of our element, we've got, or our molecule here, we've got a bunch of blue area. Okay, this means we have low electron density, and then on the other side, we've got a bunch of red area. This means it's got high electron density. And so we get this area, we get this side that has a lot of lack of electrons. So your protons from your nucleus are just kind of chilling out there. So you're going to be positive on this side, but on the other side, you got a whole bunch of extra electrons that are overpowering this part of the nucleus. So you get like a negative side over there. And so this is really what we mean by polarity. It's got a pole. So pole that's positive, pole that's negative. Just like a magnet, right? If you drew a magnet, everybody's seen magnets like this, right? And sometimes there's a line in the middle, one side's red, one side's blue, and they're labeled as north and south. Okay. And so same idea, we've got poles on this magnet, we got poles on this molecule. And then we also have lithium fluoride. Now you should know lithium fluoride is actually an ionic bond, right? Because it's a metal with a nonmetal, but notice that we get a definitively positive side over here. Big time positive and big time negative over here. There's not really a lot of sharing. Like right here at this line, notice that it gets dark red like as soon as you hit the fluorine part of the atom, and then it's got all the electrons. And as soon as you hit the lithium side, you get like absolutely no electrons. So that's really the ionic bond. Now the measurement that we use to keep track of who's pulling harder is a periodic trend called electronegativity. Okay, and electronegativity is defined as the ability of an atom in a molecule to attract electrons to itself. Okay, so it's how hard or how much is it going to pull more electrons to itself. So it's very much related to electron affinity that we talked about before, but it's its own thing called electronegativity. All right. So generally, electronegativity follows the same trend as nuclear effective charge and electron affinity and ionization energy. So it increases going from the left to the right and from down to top. Okay, so you need to have these values, okay, in order to answer a bunch of these questions about whether or not a molecule is polar, or whether or not a bond is polar. Okay, and so really, so the high electronegativities are rated from 3 to 4, then 2 to 3, and then 1.5 to 1.9, and then less than 1.5 are really not electronegative at all. Okay, notice the cesium's the lowest, and it's at 0.7. Okay, yep. So when we're comparing these two values, all we have to do is subtract the higher from the lower in order to figure out what the electronegativity difference is. That electronegativity difference is what allows us to determine whether or not our bond is polar. Okay, so if they're shared unequally, that means that there's a polar bond. We've got one side that's positive, one side that's negative. So we have two ways of representing that. Okay, so if it's there's one way where we use these symbols like this. This is a lowercase delta, okay, and it stands for partial. So this means it's partial negative, okay. And then the other one, it looks like this, and it would be partial positive, okay. And so we should put the partial positive on the hydrogen side here, and the partial negative on the fluorine side, okay. And then we can also use this symbol here, and it's just simply an arrow with a plus on the side that's positive, and an arrow points to the side with more electrons. So these are the two ways that we have to represent what's happening in our atom, or what's happening in our molecule. What's positive, what side's negative. We can use one or the other or both. All right. Okay, so polar covalent bonds, okay, so the greater the difference, the more polar it is. So notice that, so we've got this variation, and you can see just from the colors here that hydrofluoric acid is more polar than hydrochloric acid, which is more polar than hydrobromic, and more polar than hydroiodic. Okay, and so then they give you all these other values here. The electronegativity difference of hydrofluoric acid. So look at these values here. It gets the electronegativity difference value goes down, and we get that just simply by using that periodic table we saw a couple slides ago. This guy here, where we just take our number minus the other number. So 4 minus 2.1 for the hydrogen would give us the 1.9 difference. That's right here. And notice that as our electronegativity difference goes down, our bond length is going up. So there's this inverse relationship here. So hydroiodic is a bigger bond, or bigger molecule than hydrofluoric acid, and it's got a bigger bond length. We also have these dipole moments as well. Notice that the dipole moment is getting smaller with the electronegativity difference. And we'll talk about dipoles. All right. So a dipole is when we have charges separated by a distance, okay, and it's measured by a dipole moment, okay, and it uses this Greek letter mu, all right, and it's produced by two equal but opposite charges separated at a distance r, and so this is the formula to calculate dipoles, all right, and it's calculated in debye, capital D for debye, and so simply all we have to do is take the charges, the charge difference, and then multiply it by the radius, and we get that dipole moment. Okay, and so this is just a way of keeping track of what is going on in our bond. Okay, so we'll just take so like for example, this has a dipole moment of 1.82. This one has 1.08. So notice that the more polar the molecule, the bigger the dipole moment. Okay. All right, so which of the following bonds is the most polar? All right, so in order to answer this, all we have to do is look at our periodic table. So we've got HF, well, we already figured that one out. That was 1.9. Then we have HI. Well, let's jump back to our periodic table here. HI, I is 2.5, hydrogen is 2.1, so it's got a difference of 0.4. All right, then we have selenium fluoride. So we'll go back here, selenium fluoride. Selenium is 2.4. Fluorine is 4.0, so that's a difference of 1.6. 1.6. And then we have nitrogen and phosphorus. Nitrogen is 3, phosphorus is 2.1, so we have a difference of 0.9. All right, last one here, gallium and chlorine. So gallium is 1.6, chlorine is 3.0, so we get a 1.4 difference. Okay, 1.4. So the biggest difference here is going to be between hydrogen and fluorine. And we could also kind of guess that that was going to be the one that was the biggest difference as well, just purely based on their locations on the periodic table, because we know electronegativity is going to be increasing going from left to right and increasing going from bottom to top. And so that one has the biggest difference distance-wise between those molecules. So that would have been a good guess to start with as well. All right, and then in order to answer this, you just do the exact same thing. Okay. All right, last little bit here is in order to determine whether or not a compound is ionic or covalent, I primarily use just the simplest approach here that they list of first bullet point, and it hasn't really steered me wrong all that too much. Okay, so it's simply a metal with a nonmetal is an ionic compound, and then two nonmetals is a covalent compound. There are a couple of exceptions. Oxidation number can change things. If you, for whatever reason, if you're making a molecule that has a very, very high oxidation number, especially with the metals and the metals that are in the P block, if they have a high oxidation number, they can have covalent bonding, but it's pretty rare. Okay, and then electronegativity difference, you can also look at that. Okay, on the back of the periodic table, I tell you that if anything, there's a value that if I say if your electronegativity difference is bigger than a certain value, you have an ionic compound. All right, but once again, you have to look at the oxidation number to really use that effectively in all cases. Okay, but really the foolproof way to really tell whether or not you have an ionic or covalent compound is looking at the properties of the compound. Okay, so like ionic compounds tend to have very, very high melting points is one of the biggest things you can look at. So if you have a compound and you don't know whether or not it's ionic or covalent, simply taking it and putting it over a flame just to see if it melts is like on a piece of aluminum foil is a pretty decent way to tell whether or not you have an ionic or covalent compound. It's just kind of, obviously it's just qualitative as opposed to quantitative at that point, but it kind of gives you a good indication of what you're looking at. Anyway, go ahead and do your text problems and practice lots of Lewis structures and bond polarity, and I'll see you on the flip side.